Right, so Fanus spent 24 years with De Beers as a research geologist, and then he joined the University of Johannesburg to take up the DSI NRF research chair in geometallurgy. And his research interests mostly involved the study of kimberlites, diamonds, and mantle xenoliths. So Fanus, we look forward to your presentation on the characteristics, origin, and evolution of diamonds.
Right, the purpose of this presentation is to discuss the characteristics, origin, and evolution of natural diamond with you. And so by way of introduction, I'll be talking about diamond characteristics. I'll be dealing with shape, size, color, infrared characteristics. I will then follow up with a discussion of diamond genesis in terms of diamonds and kimberlite, cratons in the lithosphere, mantle xenoliths and inclusions in diamonds, diamond thermobarometry, carbon isotopes in the age of diamond. And then finally, I will finish off with a discussion of the evolution of diamond and a specific focus on diamond surface features. Right, when diamonds crystallize, they typically crystallize as an octahedron, as you can see here. And they may also be twinned, in which case you would end up with these flat macles. And so these are some examples of octahedral stones. A nice octahedral stone over there and over here, some over there. And if you look over here, you'll see a flat triangular stone, which is your typical macle shape. Moving on to cubes, if diamonds crystallize at a somewhat lower temperature, they crystallize as a cube. And that may also represent itself or present itself as a re-entrant cube, which is also likely due to twinning. Now, many of these cubes are opaque, as you can see here. Some do tend to be gem quality. For example, these two, which are from the Zwaneng diamond mine in Botswana. But for the most part, they tend to look like this, or they are individual cubes, in which case they're typically gray, or they may also have a yellowish color to them due to the comparatively low nitrogen aggregation state in them, as well as a high nitrogen content. And so moving on to coated diamonds on board. This is board, which is essentially a form of polycrystalline diamond and which is completely opaque. In fact, a lot of the time it has a sort of dark gray to black color that is crushed and used in industrial applications. When it comes to the more traditional coated diamonds, you can see some octahedra here with black coats on them. Some of the coated diamonds do actually contain a clear core, as you can see here, and that's then surrounded by this more cloudy growth zone of diamond. An example here of an octahedral stone with a coat that has been partially broken off. And here you can see a cubic stone that has some gray diamond coat on it. The other more common form of diamond is what is known as a dodecahedron. The dodecahedral form of diamond is not a crystallization form. It is actually a resorption form. And so your diamonds crystallize originally as octahedra in the mantle. As they then end up in a kimberlite and are being transported to the surface, because the kimberlite is hot and oxidizing, the diamonds are then resorbed down to the more dodecahedral form, as you can see here. And essentially what happens is your triangular faces on the octahedral stones are progressively resorbed. As you can see here, with progressive resorption, you essentially lose that triangular face and you end up with these six-sided faces, as you can see here. And these are commonly known as dodecahedral diamonds. They are actually technically more correctly described as tetrahexahedroidal diamonds. Some examples of large diamonds, that being from the Cullinan diamond mine, and that also from the Cullinan diamond mine. If you look at these stones closely, you can see that they are very typically damaged. They're typically broken. And I would imagine that much of that damage is due to the recovery process. It's very common to have a 25 millimeter spacing in the crushers, and obviously these stones are significantly larger than that, and hence likely to be damaged in the recovery process. When they are not damaged, they have these very unusual potato-like shapes, and many of these large diamonds do contain low to no nitrogen. So I would imagine that much of the shape that you see here is due to resorption in the kimberlite, but the resorption is assisted by the low nitrogen content of these diamonds to give you these unusually smooth, rounded off morphologies. Diamond color. Diamond color is typically influenced by impurities in the crystal lattice. And so, for example, if you have nitrogen structurally bonded into the crystal lattice, you would end up with a yellow color. In cases where you have nitrogen-free diamonds, but that contain boron, you end up with a marked blue color for the diamonds. Diamond color may also be influenced by defects in the crystal lattice. And so, for example, diamonds reside in the mantle at high pressures and high temperatures, where they can be easily deformed. And so if there is, for example, cratonic deformation through, for instance, mountain building processes, or for that matter, sampling of the mantle by the kimberlite may also deform the surrounding mantle, you would end up with essentially pink, brown, red, or purple diamonds due to the plastic deformation. Diamonds that are weathered out of the kimberlite and end up in the alluvial environment may be affected by irradiation when they are in touching contact with radioactive minerals. And in that instance, you get lattice damage. So it is not just surface coating, it is actually lattice damage that penetrate into the diamond for a couple of microns. And in that case, you get green spots and stains. It's important to emphasize that these green spots and stains cannot be removed through acid boiling, for example. They are there, and it's a permanent form of surface damage. Green spots and stains on diamonds may be turned into brown spots and stains through heating. And so an instance of that would be if your diamond's in a alluvial deposit, in a sedimentary deposit, is then caught up in a metamorphic process where these green spots and stains, through heating and metamorphism, is turned into brown spots and stains. And that's quite useful as an exploration tool, because if you see diamonds, abundant diamonds, with brown spots and stains, it may very well be that your diamonds have been through more than one cycle of deposition and subsequent erosion, maybe a mountain building process of some sort, and hence your diamonds could be a significant distance from source. Then diamond color due to primary inclusions. We're talking here about things like graphite inclusions as well as sulfide inclusions in diamonds. If you have an abundance of graphite inclusions or an abundance of sulfide inclusions, the diamonds are very typically gray or black. We do also find a subpopulation of diamonds which have an ivory white color or maybe opalescent. And in that instance, the color of the diamonds are most likely due to swarms of micro-inclusions that are distributed throughout the diamond. And the nature of those inclusions is still comparatively poorly understood. Some examples here are, for example, black diamonds or gray diamonds, as you can see, some examples of colorless diamonds, yellow diamonds over here due to high nitrogen contents, and some examples here of blue diamonds, low nitrogen content, along with boron contained in the crystal lattice. Some stones here that are essentially variants of orange or brown, probably due to plastic deformation. And then this peculiar chameleon green color, as you can see here, due to a combination of nitrogen in a low aggregation state, possibly combined with plastic deformation in the mantle. Moving on to polished stones to illustrate color, you can see some nice pink over here, some very typical blue over here. This would be considered fancy blue. Colorless stones over here, obviously, and then again, brown to maybe a somewhat of an orange color, as well as something here that incorporates more of a some slightly purplish tinge to the color. Over here, a stone with a sort of an olive green color. Now we can use infrared spectrometry to distinguish different types of diamond. Using infrared spectrometry, we can detect structurally bonded nitrogen, and those are known as type 1 diamonds, which are often yellow in color. And again, using infrared spectrometry, we can also detect nitrogen-free diamonds, which are usually colorless, but may also be blue if they contain boron, and these are known as type 2 diamonds. Still on the subject of an infrared spectrometry of diamonds, this is a typical infrared spectrum of a nitrogen-containing diamond. And along the horizontal axis, we have wave numbers, which is essentially the number of cycles that you have in your infrared region of the optical spectrum per centimeter. On the vertical scale, we have absorbance, which is essentially how much of the infrared radiation is absorbed by the diamond as the beam passes through the stone. Over here, we have the nitrogen region. And so nitrogen-containing diamonds, which show peaks in this region. Over here, we have a platelet peak, which relates to the movement of nitrogen through the crystal lattice as it aggregates in the diamond crystal lattice. During that migration of nitrogen through the crystal lattice, there are also clusters of carbon atoms that form, and these have a very specific vibrational bond, which is known as the platelet peak. And moving on to this region over here, these are carbon-carbon vibrational bonds in infrared spectroscopy, and it is unique to diamond. So if you have a colorless mineral and you would pass an infrared spectrum through it, and you see these peaks over here, you can be fairly certain, or you can be almost 100% certain that you are dealing with a diamond. These are carbon-carbon vibrational bonds. Over here, some diamonds do contain hydrogen, and when they do, you have carbon-hydrogen vibrational bonds, which shows up in this region of the infrared spectrum. Now, the nitrogen in diamond is originally captured as a carbon-nitrogen substitution. And that's very typical of diamonds that are very young, or for that matter, of diamonds that are synthetic in origin. Natural diamonds, because of the temperatures in the mantle and because of the mobility of nitrogen through the crystal lattice at high temperature, along with time, results in a different type of aggregation of nitrogen in these natural diamonds. And so, for example, a diamond that has crystallized fairly recently at high temperature and has had a little bit of time for the nitrogen to aggregate would have an infrared spectrum that looks like this. So this is an individual stone that I've selected specifically to demonstrate this. It contains 24% nitrogen in the highly aggregated B form. And this stone, in this specific instance, contains on the order of 300 ppm nitrogen. This is another diamond that I've selected to illustrate what a stone with somewhat more aggregated nitrogen would look like in terms of its infrared spectrum. This is known as a 1A-B aggregation state. So this would be classified as a 1A-AB diamond. It contains 73% of the nitrogen in the B component, in the highly aggregated B component, for this stone, which contains on the order of 400 ppm nitrogen. And you can see that this peak, particularly in the nitrogen region, is now more pronounced. And then finally, a highly aggregated stone, which contains virtually all of its nitrogen in the 1AB aggregation. This stone contains 98% of its nitrogen in the highly aggregated B state. This stone contains 600 ppm nitrogen. And you can now see that this peak is very pronounced. So for all intents and purposes, the height of the peak, the height of these peaks corresponds to nitrogen content, and the shape of these peaks correspond to nitrogen aggregation state, as you can see here. That being poorly aggregated and this being highly aggregated nitrogen. Now, again, this is potentially a useful tool. We do find that some kimberlites contain diamonds which are predominantly of this aggregation state. And we do recognize some kimberlites where the diamond population tends to be more dominated by this aggregation state. And that in combination with nitrogen contents, which can be highly variable between different diamond sources, allows you a tool to essentially make a call with regards to the source of diamonds from different kimberlites which have been amalgamated into an alluvial source. The other thing that is quite useful is that you can make a call with regards to how long diamonds have been resident in the lithosphere. For example, some kimberlites have an abundance of diamonds that look like this. And we think that those diamonds have been sitting in lithosphere for a comparatively short period of time, maybe on the order of hundreds of millions of years, while kimberlites that have an abundance of diamonds that look like this in terms of its nitrogen aggregation state probably contain diamonds that are somewhat older than that. But I must emphasize that the errors are huge in infrared spectroscopy. And so to use this as a speedometer in terms of dating diamonds is not particularly successful. This is an example of a nitrogen-free diamond. As you can see here, there are no nitrogen peaks present. We classify these diamonds as type 2A diamonds. And that's an example of what these stones look like. For example, these are nitrogen-free diamonds from the Letseng diamond mine in Lesotho. We also encounter these diamonds from the Karowe mine in Botswana, and that's a very typical nitrogen infrared spectrum. There are no nitrogen peaks present. When we do encounter blue diamonds, as you can see here, a nice polished stone of a fancy blue, you can see again that we have no nitrogen peaks present in the nitrogen region, but what we do see here is vibrational bonds which correspond to boron. And I would imagine that these are carbon-boron vibrational bonds. You can still see the carbon-carbon bonds over here, so we're clearly dealing with diamond, but these peaks over here are very typical of boron-containing diamonds with their marked blue color. Right, I want to move on to diamond genesis. And so if we are talking about diamond genesis, we have to discuss diamonds and cratons. This is a map, a global map, with the red areas here essentially outlining the oldest parts of these various continents. And so if you have areas of the world where the continent, the cores and nuclei of these continents contain very old rocks, and particularly Archean rocks, on the order of 3 to 3.8 billion years old, these are the regions that are known as cratons. If we look at these cratons in detail in terms of diamondiferous kimberlites, you can see that many of these cratons contain diamondiferous kimberlites, of which, of course, there's the classic one, the Carval craton over here. And then we also have regions where there are diamondiferous lamprites. This forms the basis of diamond exploration, and it's based on something that was originally recognized by Tom Clifford, probably by now a generation ago, and it's commonly known as Clifford's rule of diamond exploration. Now, why is this the case? And so what I want to do here, I want to take you on a journey through old continents, and particularly what lies underneath the oldest parts of continents, which are known as cratons. Over here, we have a vertical scale. This goes down to 400-kilometer depth. In this region, we have an area which is known as the lithosphere, which is old, cold, and very thick. And it is underlain by something which is known as the asthenosphere, which is hot and presumably oxidizing, and hence we will not have diamond present within the asthenosphere. In the case of the lithosphere, on the other hand, we have a lower boundary over here where diamond may be present on top of it. Below this boundary, we have the asthenosphere, which I've said before is hot and oxidizing. Within this region, we have an upper boundary, which is essentially the graphite diamond in inversion curve. Above here, you will have graphite present. Down here, you will have diamond present. This region, therefore, may contain diamonds. We do think that the diamond distribution of the lithosphere is not necessarily homogeneous, that it is quite heterogeneous, primarily because we do find kimberlites that have penetrated this region, but that do not contain diamonds. And so, to take that a bit further, it would appear that much of the diamond budget within the lithosphere could very well be due to the passage of fluids into this lithosphere, presumably from emanations out of the asthenosphere, or maybe even from degassing of the core. Another source of these fluids may very well be that we have plumes coming up from the asthenosphere or from the core mantle boundary or the upper mantle, lower mantle boundary. And these plumes may also impact on the lithosphere and release fluids, which may again result in diamond crystallization. The other thing to note is obviously that you have subduction zones over here on the edges of continents. Those subduction zones may also carry oceanic carbon into the subduction regions, in which case there may be a case to be made for a link between subduction and the crystallization of diamond, which I will explore a little bit further later on. The graphite diamond transition here dips towards greater depths along the edges of the cratons as you start going into the off-craton regions. And the reason for that is that the heat flow from the asthenosphere becomes more pronounced in these regions. So these regions of continents are significantly hotter than these cold and very thick regions of the lithosphere in the centers of continents where you have your oldest rocks and therefore have your cratonic regions. And so any kimberlite that passes through these regions of continents are likely to be barren because we're essentially dealing with an off-craton environment. And any kimberlite that passes through this part of the oldest regions of continents, which are underlain by old, cold, and very thick lithosphere, could potentially be diamondiferous. Right, so if we move on a bit with regards to the rock types that makes up the lithosphere, this is a diagram demonstrating the abundance of olivine, orthopyroxene, and clinopyroxene as a classification scheme. And so if you have rocks that consist of orthopyroxene, clinopyroxene, and olivine, they would be considered to be lertzolites. Rocks that consist of orthopyroxene and olivine we call hartsbergites, and particularly in the case of the lithosphere, hartsbergite and lertzolite makes up the lithosphere, and these two rock types in combination is known as perudotite. They both may contain accessory garnet, and they both may contain accessory spinel. The spinel may be either an aluminous spinel, or it may also be a chrome-rich spinel. It is commonly assumed that hartsbergite is essentially a highly depleted form of lertzolite in that it does not contain clinopyroxene, and it also contains significant chrome and very low calcium contents. And hence the minerals that occur in the hardspergite tend to be very chrome rich, but tend to have comparatively low calcium relative to leutzolite, which contains clinopyroxene, which is full of calcium. We also distinguish another rock type within the lithosphere, which is known as pyroxenite, consisting predominantly of orthopyroxene, as well as clinopyroxene. And if pyroxenite contains a certain amount of chrome, we call them websterite rather than pyroxenite. And then finally, over here, if you have a rock consisting of olivine as well as clinopyroxene, that rock would be known as a whorlite. So if we move on from this, this is very typical and of what we find in kimberlite in terms of xenoliths derived from the lithosphere. Remember, we cannot access the lithosphere. You're looking at rocks that are sitting at 150 to 200 kilometer depth. The base of the crust is on the order of about 65 kilometers. And so we cannot physically access these areas. We have to look at xenoliths that comes up in kimberlites. The peridotite xenoliths that comes up in kimberlites consist of garnet as well as orthopyroxene and olivine, all of which these are highly magnesian. The garnets in particular contain low chrome, or may contain low calcium, and will contain high chrome. If we are dealing with leutzolites, there will also be a certain amount of clinopyroxene present in this rock. But these are essentially high chrome lithologies. The other rock type that we find as xenoliths in kimberlite is eclogite. Remember I said we have subduction processes. Subduction processes most likely bring oceanic crust into the lithosphere, and hence we have eclogite forming. Eclogite is a low chrome rock type, which has high iron content. And so you have orange garnet, as you can see here, and you have a sort of a khaki green clinopyroxene, as you can see here. This is a low chrome rock type, and it tends to be iron rich. Now, there's a close link between these rock types and diamonds, in that if we look at diamonds, we break them open and we pull out the inclusions that occur in them, we can classify both a peridotitic suite of diamond as well as an eclogitic suite of diamond. And so, for example, here is a diamond that contains a chromite inclusion, and hence we would consider this to be a peridotitic diamond. Here is a diamond that has a purple garnet inclusion. That garnet has low calcium content and high chrome content, and hence we would consider this to be a peridotitic diamond, and particularly a hardspergitic diamond. Over here we have an eclogite with orange garnet, and the eclogite has a little diamond embedded in it. Here we have another eclogite, again with orange garnet, and it has a diamond embedded in it. This is a diamond with an orange garnet inclusion in it. That orange color is a sure enough indicator that you are dealing with an eclogitic garnet sitting in this diamond, and hence we consider this to be an eclogitic paragenesis diamond. There's a fragment of eclogite, a fragment of peridotite because of the color of the garnet over here, and it is diamond bearing. Over here we have another diamond bearing eclogite, and over here we have a diamond with a sulfide inclusion in it. Now, these sulfides in diamonds are quite interesting because we can distinguish peridotitic sulfides, which have high nickel, and we can also distinguish eclogitic sulfides, which have low nickel. Hence, we have peridotitic diamonds with sulfide, and we have eclogitic diamonds with sulfide. Much of this diamond research have now resulted in a significant database. If we interrogate that database in terms of diamond paragenesis, we find that the global database comprises of predominantly peridotitic diamonds, followed by a much smaller abundance of eclogitic diamonds and a very small abundance of websteritic diamonds. So what I'm trying to say is diamonds that contain inclusions are predominantly peridotitic because they contain peridotitic inclusions. the suite of eclogitic diamonds contains eclogitic inclusions, and the suite of Websteritic diamonds contain Websteritic inclusions. Then we also have a very minor sublithospheric suite of diamonds, which are very unusual and bear no resemblance to this lot. These diamonds are from great depth within the asthenosphere, probably brought there through subduction processes where the pressures are so high that, for example, the garnet contained in these diamonds contain clinopyroxene in solid solution in them. This is still the subject of much research. If you are interested in that, I would refer you to this paper, and I would argue that the nature of these sublithospheric diamonds is still comparatively poorly understood. If we break up the peridotitic suite of diamonds into these components, we find that 86%, so the majority of peridotitic diamonds, are actually of a hard-spaghetic paragenesis, while a comparatively minor proportion of peridotitic diamonds are of a litholitic paragenesis, and then, quite frankly, a vanishingly small population of the peridotitic diamonds are of a whorlitic paragenesis. If we look at that classification in more detail by interrogating the chemistry of garnets occurring as inclusions in diamonds in terms of their chrome content as well as their calcium content, you can see that we essentially have two fields on this diagram, one of which represents peridotitic garnets occurring as inclusions in diamonds. And the vast majority of those peridotitic garnets occurring as inclusions in diamonds plot to the left of what is known as the Gurney line. So on the order of 85% of peridotitic garnets occurring as inclusions in diamonds plot in this field over here, which is known as the Hartsbergite field. This forms the basis of much of the world's diamond exploration. If you find garnets in your prospecting program that plot somewhere in this part of the diagram, then the assumption is, because of the fact that they are so abundant as an inclusion in diamonds, that you are potentially onto a potentially diamond-bearing kimberlite. And the theory of that is discussed in these two papers. Within this field, we also distinguish what is known as low calcium hardsbergites. For example, less than 2% calcium would classify a garnet as a low calcium garnet, and therefore those would be known as low calcium hardsbergitic diamonds, which is a bit of a misnomer, but it serves the purpose. And then over here, this region of the hardsbergite field, we classify as the more calcic hardsbergitic garnets, and hence we also distinguish more calcic hardsbergitic diamonds. Over here is what is known as litholitic garnets, and hence those are known as litholitic diamonds if you have a diamond that contains garnets that have these chemistries in them. Over here is a field of eclogitic garnets occurring as inclusions in diamonds, and hence we would call these diamonds eclogitic diamonds. That is an example of a diamond containing whorlitic inclusions, and over here we have examples of diamonds containing Websteritic inclusions. I want to move on to chromite in diamond. That is another very common inclusion variety in diamonds. And if you look at their chrome and magnesium contents, you find that they have high chrome, between about 60 and 70 weight% chrome, and on the order of about 11 weight% magnesium to about 17% magnesium. And again, this forms a prospecting tool because you see an abundance of chromites in diamonds, and those diamonds are peridotitic diamonds because this is a peridotitic mineral because it has this high chrome content and this high magnesium content. If you start seeing these chromites in your prospecting, there's a possibility that these chromites could be from diamond-bearing kimberlites. But it's a lot more complicated than that, because you can see the same chemistry is also in chromites from the Bushveld complex, for example. There will be presentations dealing with this at a later stage. These same chromites occurring as inclusions in peridotitic diamonds also contain low titanium content. So again, if you see high chrome and high magnesium and low titanium in chromites in your prospecting program, that's potentially, with a little bit of complication involved in it all, that's potentially from diamond-bearing kimberlite. And hence you may be able to sell that prospect on the stock exchange. Now, it is possible to determine the pressures and temperatures at which diamonds crystallize by using coexisting minerals. If you have coexisting minerals occurring as inclusions in diamonds, as they are sitting in the mantle and as they are being captured by the diamond growth event, the diamonds will record, or at least the inclusions in the diamonds will record the particularly the temperature, but also the pressure at which those diamonds were crystallizing. And essentially what you do is you look at things like nickel thermometry in the case of garnet olivine exchange, or you look at aluminium barometry in the case of orthopyroxene garnet exchange, and so on. If we make use of these various thermometers and barometers, we can determine that diamonds crystallize at pressures of on the order of 50 kilobar to 70 kilobar, which corresponds to depths on the order of 150 kilometers to about 200 kilometers. And if you look at the temperatures range from about 1,000 degrees Celsius to 1,200 degrees Celsius. This is the graphite stable field. There are uncertainties with regards to the temperatures and pressures that you can calculate, which is pure error bar. But for the most part, our diamonds plot in this region in the diamond stability field, and they sit at comparatively low geothermal gradients. These are geothermal gradients, which is essentially the heat flow through the lithosphere. Within thick lithosphere, the heat flow is comparatively low because the lithosphere is thick and serve as essentially a thermal insulator from the hot asthenosphere. And so at geothermal gradients on the order of about 38 to 40 milliwatts per square meter at surface, you have the right type of conditions for diamond to crystallize. If you have higher geothermal gradients, for example, more than 42 milliwatts per square meter, you will end up in a region where your diamonds, having crystallized originally, if this is a heating event, your diamond will be destroyed again. But essentially for our purposes, if you're looking at thermal gradients of about 38 milliwatt per square meter, that's where your diamonds will be stable. Right, how do diamonds crystallize? We think they crystallize as a series of pulses, and we know that because you can cut a diamond into plates. It's a very simple process. And then if you look at the diamonds, if you look at the interior of the stones using cathodoluminescence, if you irradiate diamonds with electrons using an electron gun, you get what is known as cathodoluminescence. The diamonds essentially glow under the electron beam. And so you can see the internal stratigraphy of the diamond. For example, this diamond has a core which may even have suffered a tectonic event, in which case it may have deformed. It then healed in a subsequent regrowth event, as you can see here. In this case, we have a core to the diamond. That's probably the initial seed on which the rest of the diamond grew, probably through a series of volatile pulses. You can see the same kind of process over here. Note the pulsed type of growth of this diamond, and the same type of thing here. So essentially what this means is that diamonds tend to grow like an onion would grow. It starts off with a core, And then if you have a variety of growth events, which might be related to intermittent fluid flow through the lithosphere, you get progressive diamond growth. Now, because diamond is essentially 99% carbon, you can look at the carbon by burning the diamond and putting that gas then through a mass spectrometer to determine the carbon-13, carbon-12 isotopic composition of diamond. If we do this for peridotitic diamonds, you find that the carbon isotopic composition is comparatively restricted. If we do this for eclogitic diamonds, you find that the carbon isotopic composition is of quite a large range. And some of this carbon isotopic composition correspond or overlap with the carbon isotopic composition of organic matter. And some of this range in carbon isotopic composition also correspond to the carbon isotopic composition of carbonates. For example, carbonates that you might find on the ocean floor associated with pelagic sediment, or for that matter, associated with alteration of oceanic crust. The carbon isotopic composition of organic matter may correspond, for example, to bacteria associated with thermal activity on the ocean floor. And so it would appear that in the case of eclogitic diamonds, there's a strong case to be made for the subduction of organic matter as well as carbonates into the deep regions of the Earth, say at the base of the lithosphere, through subduction of oceanic crust. However, in the case of the peridotitic diamonds, we have to look at this in somewhat more detail. And so if we, for example, model diamond crystallization using theoretical models of the fractionation of carbon isotopic compositions between methane and diamond and carbonate or carbon dioxide and diamond, we can model that the bulk of hard spagitic diamonds probably crystallize from some form of methane, with a more subordinate population of hard spagitic diamonds crystallizing from probably carbonates, maybe carbonate-bearing melts or fluids. And if we look at the lertzolytic diamonds in more detail, we can model that, excuse me, that maybe a smaller population of lertzolytic diamonds crystallize from methane, while a more enhanced population of lertzolytic diamonds crystallize probably from carbonates in melts or fluids. Now, that's not necessarily the whole story. Through thermodynamic modeling, it is possible to demonstrate that it may very well be the case that diamonds crystallize from water-rich fluids that form within the lithosphere and which may have its source within the asthenosphere. But for the present purpose, that we are essentially dealing with water-rich fluids that contain methane as well as carbon dioxide, and we can demonstrate thermodynamically that these fluids would be in equilibrium with diamond. However, depending on compositions and as the temperature changes, as these fluids move through the lithosphere from the high temperature environment into the lower temperature environment, in that flow along the geothermal gradient, you potentially crystallize diamond from these fluids. And so if you have pulses with time, with geological time, for whatever reason, of these fluids, you progressively crystallize diamonds that then become progressively bigger and bigger as they have more contact with these fluids over geological time. Now we can date diamonds. We know how old diamonds are, or at least we know how old diamonds are that are inclusion bearing by using isotopic systems like, for example, the samarium-neodymium system, looking at the samarium neodymium system in garnets as well as kleiner pyroxenes occurring as inclusions in diamonds. And we can also make use of the rhenium osmium system for sulfide-bearing diamonds to gain an insight into the age of diamond. So if we date hard spaghetic diamonds, and I'm not talking specifically about diamonds that contain purple garnets in them, that have calcium contents less than 2 weight%, and have chrome contents that are in the order of 10 to 20 weight% chrome, those diamonds typically come out with an age which is Archean, and essentially ages that are in the order of about 3 billion years or so. On the other hand, if you date eclogitic diamonds, and you look, for example, at the samarium neodymium system for eclogitic diamonds that contain inclusions of garnet and kleiner pyroxene, we find that these eclogitic diamonds very typically report a Proterozoic age of diamond crystallization. Those eclogitic diamonds tend to start showing these ages at about 3 billion years or so. And so the assumption is that eclogitic diamonds start forming in the late Archean and particularly form in the Proterozoic, probably because Archean processes started to cool down around about here. Over here in the early Archean and particularly in the Hadean, the Earth was still very hot. Temperatures started to drop until we got to about here in the late Archean, and by which stage it was possible for subduction processes to start taking hold at the Earth's surface. And hence, at that time, we were subducting oceanic crust into the base of the lithosphere, and hence there is the option for eclogitic diamonds to start forming in the late Archean and particularly in the Proterozoic. The inference is that these hard spaghetic diamonds, and particularly these highly depleted hard spaghetic substrates in which these diamonds were crystallizing, formed in the Archean through the extraction of komatiite, probably in plume processes that was very prevalent in the Archean. And then in that time, our cratons were forming. And because of the passage probably of methane through this type of material, we were crystallizing these highly depleted hard spaghetic diamonds. Where it gets more complicated and where it gets more uncertain is in the case of litholytic diamonds, as well as the more calcic hard spaghetic diamonds. What I mean by calcic hard spaghetic diamonds is these diamonds contain purple garnets, which are peridotitic, but those garnets are comparatively calcic. They sit fairly close to the Gurney line. And particularly with the recent advent of high precision dating, which was applied about 5 years ago to the Venetia chemolite, where a team at the university, the Free University of Amsterdam, looked at the age of highly depleted hard spaghetti occurring as inclusions in diamonds, which proved to be 2.95 billion years old, and looked at more calcic hard spaghetti occurring as inclusions in diamonds, also from Venetia, but the more calcic hard spaghetti produced an age of 1 billion years. And so at the moment, the thinking is that litholytic diamonds and the more calcic hard spaghetti diamonds are essentially a Proterozoic diamond source, which probably forms in the Proterozoic through presumably plume processes, which normally result in large igneous provinces, but in the case of the lithosphere, also shows a link between large igneous provinces and the crystallization of litholytic diamonds, as well as more calcic hard spaghetic diamonds. This is all very new, and the technology is currently being applied to, or maybe I should rather say, this technology really needs to be applied more to, for example, places like the Premier chemolite, where we also see these calcic hard spaghetic diamonds And I'd be very interested to see what happens there if we apply the more modern high precision dating to those diamonds. Right, let's move on to the evolution of diamonds. And here I specifically want to talk about diamond surface features. If you look down the octahedral direction of a diamond, if you look down the octahedral crystallography of diamonds, you see very specific sets of surface features. For example, trigons, hexagonal pits, and shield-shaped laminae, which is unique to the octahedral direction. If, on the other hand, you look down the cubic crystallographic direction of diamond, you see things like tetragons and crescentic layering, which is again unique to the cubic direction. On the other hand, if you look at dodecahedral diamonds, you see a whole horde of surface textures, and dodecahedral diamonds obviously are the more resorbed form of the primary crystallization forms. And so here, there is no uniqueness in terms of crystallographic direction. What you see is things like terraces, hillocks, low relief, ribbing, and so on. And then finally, if diamonds are released from the kimberlite during weathering and they end up in the surface environment, you may see things like abrasion, percussion, scar, polish, and network pattern, for instance. So what are the agents in producing surface features? Well, first of all, diamond growth, crystal growth would be an agent in producing surface features because we can see the internal stratigraphy now.
5 minutes, Fanus.
Thank you, I'm almost done. Inclusions in diamonds also has an effect on the crystal growth. Twinning has an effect on crystal growth. And remember, we're talking about octahedral stones and cube stones. Mantle residence may also have an effect on the development surface features. And here I'm specifically referring to plastic deformation. If the diamond is plastically deformed and you then pick out the plastic deformation through resorption, you will end up with, for example, lamination lines. Resorption in itself, occurring at high temperature as the diamond is taken to the surface by the kimberlite, will result in a specific set of surface textures. And if we have comparatively lower temperature resorption, you'll see another set of surface textures. Resorption during passage from mantle to surface will obviously affect the diamonds and give us further surface textures. And then if your diamond is sitting in a root zone, for example, or a dike, which takes a bit longer to cool down relative to rapidly extruded volcanic clastics, you will see other surface textures that form. And then finally, if there is transport within the surface environment after the diamond is released from the kimberlite, you have things like alluvial surface textures of surf zone abrasion, wind abrasion, or for that matter, maybe scratch-like markings in the case of glacial transport. It's important again to take note of this diagram. These diamonds are octahedral, poorly resorbed or comparatively little resorbed, and will be dominated by octahedral surface features, while your dodecahedral diamonds, which are highly resorbed by the kimberlite, with no crystallographic orientation in terms of surface, those stones will be characterized by the more dodecahedral surface textures. And so some examples, these are trigons on the octahedral surface of a diamond. Those are what are known as negative trigons. They form at high temperature. You can also see positive trigons where the shape will follow the outline you're seeing here. And those are at somewhat lower temperatures. These are hexagonal features, again, which may be seen on octahedral faces. Still on the subject of octahedral diamonds in the octahedral crystallographic direction, in this case, the growth layers are picked out by the resorption. You can clearly see the individual growth layers, which are now exposed because of the resorption, and the same type of thing there. And then in the case of highly resorbed dodecahedral diamonds, you very typically see things like elongated hillocks, as well as terraces over here. And a nice example there of terracing. And then very typical of diamonds from root zones of kimberlites, which is in a magmatic environment, as well as diamonds from dikes, where you can see these circular features, which are known as microdisc patterns. We think that in these root zones and in dikes, there is an abundance of volatiles exolving from those root zones as they are cooling down. And in that case, these gas bubbles that form within the cooling kimberlite also serves to protect the surface of diamonds from resorption. And so even though there is resorption, you do see these micro disc patterns. And again, that's quite a useful prospecting tool. If you have an alluvial deposit with an abundance of these micro disc patterns, it might just be that you are looking for a kimberlite dike as opposed to a pipe. And then finally, in terms of transport, if your diamonds are eroded out of the kimberlite and end up in the alluvial environment, initial transport will show up as points and sharpest edges abrasion, with an increase in abrasion, which could or might be due to an increase in distance from the primary source. You see more abrasion, which becomes progressively more pronounced, as you can see here, until eventually, with distal transport, you have these ground down surfaces, which is also the type of thing that you might see in, for example, surf zone abrasion. You do have to be a bit careful with this classification scheme, because obviously, if you are caught up in potholes and things, then the distance aspect in terms of distance from source does not apply. And that's it. Thank you. Any questions?
Okay,
Fanus. I get load shedded.
Yeah, unfortunately we have. Fanus, I'll kick off. I'm particularly, or have always been fascinated by those pictures of diamond growth, and you know, we all know that there's been a tremendous amount of work done on, you know, mostly small diamonds, but how big is the biggest stone that, you know, people have actually dissected? Have we really dissected a large or portions of a large type 2A diamond, you know, these big white stones?
Yeah, you know, it's the old story. If you're dealing with the big stones, nobody wants to give it to you because they're quite precious. Sure. So when it comes to the really big stones, look, all we can really say at this stage, there is a hint that the big stones may have an asthenospheric root to them. But in terms of how old they are, they do not contain nitrogen.
Yeah.
When we do see nitrogen in them, which typically is at a fairly low concentration, that nitrogen tends to be highly aggregated. So it does appear that they are probably from quite a high temperature environment, or they are potentially very old. But, you know, that type of thing starts taking us also into that region of sublithospheric diamonds. And at this stage, we're not entirely sure that sublithospheric diamonds really are from the sublithosphere and great pressure. They may actually be from some very unusual lithospheric sources that is poorly understood. For example, carbonates sitting in the lithosphere. So I don't really want to stick my neck out there. Simply, when it comes to the big stones, we actually don't know how old they are.
Yeah, no, it's a fascinating one, and I guess we're going to get onto the clippers with Andy Moore, so watch the space.
Yeah, it's worth exploring, and Andy has actually put quite a lot of thought into that. So let's have a look at his presentation tomorrow.
Yeah.
And Andy has a question right now, I assume. Andy?
I beg your pardon. Thanks for that presentation, Fanus. Excellent. And I liked your comment about the deformation being linked to the actual kimberlite intrusion. And that's sort of what Mercier said about the sheared peridiotites. That,
right. Yes,
that is also...
Exactly, yeah.
So would you link that? I mean, would you be happy with Mercier's interpretation?
Very much so, because I mean, obviously the diamonds are plastic in the mantle. And so if you have, for example, an ocean island basalt plume that burns its way into the base of the lithosphere, and you then convert that plume into kimberlite through the assimilation of maybe a carbonate sitting in there, which is one model for the generation of kimberlite, that process is likely to be an extreme process in terms of mantle deformation. So it would not surprise me if much of the plastic deformation that we see for diamond is due to this process of kimberlite initiation within the deeper reaches of the lithosphere. Yeah.
We've got a question in the chat by Jürgen, I think it is. How does the occurrence of diamonds of Archean age fit in with the supposedly high geothermal gradients in the early lithosphere?
Yeah, that is very true. When I say high temperatures, I don't mean ridiculous temperatures. Once you start going into geothermal gradients where you are actually totally inside the graphite stability field, I don't think the temperatures in the Archean was that hot. In the Archean, one probably quite realistic model for the formation of the lithosphere is that you have plume activity in the Archean, which started to die down towards the late Archean, at which stage subduction starts taking hold. But because of that plume activity, as these plumes rise through the asthenosphere, they melt. It's essentially melting related to the pressure release. And so we produce komatiites. But in that process, you also produce a residue which has lost a certain amount of its iron. And hence you start forming essentially rafts, which then floats to the surface and forms the proto-continental nuclei. And those things would already have lost quite a lot of heat and would actually have served as a type of cork that essentially shields that substrate itself from the asthenosphere. And hence one could argue that, yes, the temperatures are higher in the Archean, but it was still low enough within these lithospheric rafts for diamond to actually be stable. So far, we haven't actually seen any evidence that the Archean diamonds have higher temperatures in terms of the inclusion thermobarometry than what we see for the temperatures in the Proterozoic diamonds. So all I can say is, yes, the temperatures are higher, but it wasn't high enough for diamond not to be stable.
Yeah, just to add, Fanus, it's a good question and a good answer. And I mean, you might just point out, that we found diamonds coming out of the Wits conglomerate. So those diamonds must have come from a source, older than what, 2.9. So, 2.9 billion. So, you had an environment back then, maybe not sort of from certainly not from 4.6 to maybe, 3.8, but you certainly thereafter had an environment in the Archean or Hadean to, form diamonds, preserve diamonds and get them to surface.
Yeah, exactly. You also have to deal with the formation of the moon, which may have resulted in remelting of the proto-Earth. So it gets a bit complicated within the Archean. And so we stick to the sort of middle Archean. The early Archean, and particularly the Hadean, there's very little really understood about that, apart from, of course, the Jack Hill's zircons at 4.2 billion years.
And I mean, as the technology gets better, particularly in, radioisotope dating, and that I guess will sort of, unravel a bit more, going back a bit older in time.
Yeah, I do think the advent of high precision dating, where it's now possible to deal with one diamond at a time, is, it's really very exciting. And I do think much of the Archean model, as is already seen at Venetia, is going to be refined, and we will definitely be seeing more in the way of the calcic Hartsbergites and the electrolytic diamonds, that picture is likely to become a lot clearer. There also appears to be processes like, for example, craton rifting and then subsequent annealing, which may also require modification of the classic diamond exploration model.
Fanus, would you like to comment on the relationship between micro and macro diamonds? This
Hi,
would be of
Craig.
interest.
Yeah, look, in a nutshell, the micro diamonds tend to be predominantly octahedral, probably because they have been shielded from resorption by being included in xenoliths as well as xenocrysts, and therefore they're not destroyed by the kimberlite. Well, of course, macro diamonds are extensively resorbed by the kimberlite. But apart from that, and looking at carbon isotopic compositions, I cannot see any reason why micro diamonds should be any different from macro diamonds in terms of their genesis. And hence, I think that is primarily why the micro diamond predictions in terms of macro diamond grade tends to be reasonably successful. Where you do have to be careful, though, is it may very well be the case that when you're dealing with a micro diamond population that you're doing your grade predictions with, that those micro diamonds may be somehow skewed towards a very specific population, which in that instance might very well be eclogitic. And you're now trying to predict a mixed eclogitic peridotitic macro diamond grade. And if that is the case, you know, yeah, you may very well find that your micro diamond grade predictions is not as accurate as you would like them to be.
No, just to say thank you once again to speakers and also for the delegates for staying so late in their day and starting early in their day, those who come from Canadian side.